Hello everyone! In this video, we will be learning some applications of Taylor series. In particular, we will discuss approximating a given function with one of its Taylor polynomials, and then we'll try to get a handle on the error we get in this approximation. Before that, recall that we already have a way to approximate functions, namely the linear approximation. The linear approximation of a differentiable function f near a point A is given by f of x is approximately equal to f of a plus f prime of a times x minus a. In essence, the linear approximation approximates the function f by its tangent line at a. Near the point A, this approximation may be sufficient, but it quickly becomes less and less accurate, unless of course f was a linear function. So how can we get a better approximation? The tool that we're going to use is the nth Taylor polynomial for f. So suppose that f has infinitely many derivatives at a, and that f of x is the sum of its Taylor series near a. If you're feeling uncertain about these topics, you can always go back to LectureH for a quick review. Once we have found the Taylor series for f, we can approximate f of x near a using the first few terms of its Taylor series. That is, f of x is approximately equal to the nth Taylor polynomial, which we're going to denote by t sub n of x, which is equal to f of a plus f prime of a over 1 times x minus a plus f double prime of a over 2 factorial times x minus a squared, and you keep adding terms all the way until you get up to the nth derivative of f at a over n factorial times x minus a to the n. And this is going to be the way that we approximate functions. Also, notice that t sub 1 of x is exactly the linear approximation we saw before. Let's see some examples of Taylor polynomials. First, let's estimate the values of e to the x on the interval -4 to 4 using the 4th degree Taylor polynomial centered at 0. In order to calculate the 4th degree Taylor polynomial, we will need the first 4 derivatives of e to the x, which happen to all be e to the x. And then, plugging this into the general formula for the 4th degree Taylor polynomial, we get that t sub 4 of x is equal to 1 plus x plus 1/2 times x squared plus 1/6 times x cubed plus 1/24 times x to the 4th. To see that this works, let's take a look at the graph of e to the x and t sub 4 of x. Notice that really close to 0, these graphs are very close, but then begin to separate as you get further from 0. Next, let's go ahead and do the same thing except with the 10th degree Taylor polynomial. Well, we've already done about half the work. The 10th degree Taylor polynomial will start off exactly the same as the 4th degree Taylor polynomial, and then it'll have some higher order terms. Now, let's take a look at the graph of e to the x and t sub 10 of x. Notice that t sub 10 of x stays closer to e to the x as you get further from 0, and this is exactly the reason we would take higher order Taylor polynomials, to get a better approximation in our given interval. Let's see some more examples using Taylor polynomials. First, let's find the Taylor polynomial of degree 3 for the function f of x is equal to sine of x at the point a equals pi over 2. In order to compute up to the 3rd order term, we will need to compute the first 3 derivatives of sine of x at pi over 2. So let's go ahead and do that. If f of x is equal to sine of x, then after taking 3 derivatives, we get that f prime of x is equal to cosine of x, f double prime of x is equal to negative sine of x, and f triple prime of x is equal to negative cosine of x. Then, plugging in pi over 2, we get that f of pi over 2 is 1, f prime of pi over 2 is 0, f double prime of pi over 2 is negative 1, and f triple prime of pi over 2 is 0. Plugging this all into the formula for the 3rd degree Taylor polynomial, we find that t sub 3 of x is equal to 1 plus 0 over 1 times x minus pi over 2 plus negative 1 over 2 factorial times x minus pi over 2 squared plus 0 over 3 factorial times x minus pi over 2 cubed. And if we forget the terms that are 0, we get that this is equal to 1 minus a half x minus pi over 2 squared. And so this is the 3rd degree Taylor polynomial for sine of x at a equals pi over 2. Now, for the next example, let's use this Taylor polynomial of degree 3 to estimate sine of 49 pi over 100. Notice that 49 pi over 100 is very close to pi over 2. So, since the Taylor polynomial we just computed is centered at pi over 2, it should give a pretty good estimation for sine of 49 pi over 100. Better than, say, the estimation we will get using the third degree Taylor polynomial centered at 0. So, how do we use the Taylor series to estimate sine of 49 pi over 100? Well, the problem tells us to use the approximation sine of 49 pi over 100 is about equal to t3 of 49 pi over 100, which, if we plug 49 pi over 100 into the polynomial we found in part A, we find that this is about equal to 0.9995. So that is how we will use the Taylor polynomials to approximate functions.